This lecture will be on Planck units and its significance. The earlier lecture was on natural units. In the earlier lecture entitled P2a, we emphasized and described what we mean by natural units. Natural units are used in particle physics, and setting c equal to 1 and h cross equal to 1 is referred to as working in natural units. Also, we showed that in natural units, the mass can be expressed in terms of energy, namely GeV. Length can be expressed in terms of energy inverse, namely GeV inverse. Time can be expressed in terms of energy inverse, GeV inverse. And the conversion factors were deduced in this lecture. Let us bring to discussion the fact that there are lots of constants which are used in physics. For instance, mass of proton having this amount of value, charge of electron which is minus 1.610 raised to the power minus 19 coulomb. Mass of electron is another fundamental constant, as we say. The ratio of mass of proton and mass of electron is another very important quantity, which is nearly 2000. And also there are so many constants like the H alpha Balmer line, which corresponds to transition of an electron from third level to second level, and as a result we have a radiation which is of value 656 nanometer in air and is called H alpha Balmer line. So this is again a constant. Now all these constants are somehow related to certain objects. For instance, the Balmer line, this is related to hydrogen. For instance, mass of proton, so we are referring to a proton and not to an electron. But when we are speaking of electron, then we are not referring to proton or neutron. So all these constants are somehow connected to a specific object, and they do not apply to every object of the universe. What is true for a proton is not true for a neutron or electron, and so on and so forth. So there is no universality, and in this sense they are not fundamental. They do not give information about universe. Let us speak of another constant which is called Boltzmann constant, and its value is written over there, 1.3810 raised to the power minus 23 joule per Kelvin. So it's energy by temperature. Now this Boltzmann constant is an extremely important constant in physics that is widely used, and it links temperature with energy, as well as it links entropy with probability. Now energy per degree of freedom of an ideal gas at equilibrium is given by half kT, while the entropy is related to thermodynamic probability through this relation, and this holds for isolated system in equilibrium. Now again, this Boltzmann constant also does not give information about universe, and as we see in these equations of energy per degree of freedom is half kT and S equal to KL and omega, there are certain conditions for its validity. Ideal gas at equilibrium, here isolated system, equilibrium. So certain things have to be specified when we work with Boltzmann constant. Let us now briefly mention about SI units. There are 7 SI units starting with kilogram, meter, second, and so on. Now, what is the definition of a kilogram? Kilogram represents some amount of mass. Meter represents a certain length. Second similarly represents a certain amount of elapsed time. Now this certain amount of mass, certain amount of length, or certain amount of elapsed time was defined historically and has no basis. What if kilogram from today is defined as a larger amount of mass? A meter, instead of the specified amount which we all know, 100 centimeter, which we all know, is taken to be a shorter length. We can also change our definition of second from today and take a bit longer period of time as 1 second. So this means that this SI system was defined with a historical background. There was no basis at all, and we could proceed with other options with no problem at all. Now we want to define units without historical influence or significance, and in a very fundamental and logical way. Our nature, our universe, functions in such a manner that there are certain universal constants G, H cross C, and they do not depend on object, location, time, phenomena, or situation. They are eternally valid and universally respected. And this G, H cross and C, they are fundamental constants. They apply throughout the universe. They apply to all objects. And here, history has no role to play. Now if we express mass, length and time in terms of G, H cross and C, then obviously the description will be fundamental, because these constants are fundamental. Now let us try to express MLT in terms of GH cross C through a method which is known as dimensional analysis. First, from Newton's law of gravitation, we can write it out, and from here we can find G, and if we put the units, we get this as the dimension of G. In a similar way, starting from Heisenberg's uncertainty relation, we can put the dimensions of x and p to end up with the dimension of h cross to be of this one, and the dimension of C is obviously LT inverse. Now with this background, let us try to express MLT in terms of GH cross C. And what we do is, instead of MLT taken separately, on the right hand side we can express them as G raised to the power alpha, H cross raised to the power beta, and C raised to the power gamma, where alpha, beta, gamma are to be determined. So this is the standard method of dimensional analysis. For instance, take the first equation and then we'll put dimension of both sides, and we will end up with three equations, one in M, one in L, and the other one in T. So the first task which we will do is we'll put the dimension of G, dimension of H cross, and dimension of C, and raise them to the power alpha, this one to the power beta, and this one to the power gamma. And on the left side, instead of M, in the first equation, instead of M we'll put M L0 to t to the power 0, and here M raised to the power 1. When we are considering the second equation, we'll put L to the power 1, but the other two raised to the power 0. While when we are considering the third equation, we'll be putting t to the power 1, but M to the power 0, L to the power 0. Suppose we wish to find M, then we have to take the first equation, first one in the left side, and the right hand side is the same one which will occur for three equations. So let us equate minus alpha plus beta to m to the power 1. So minus alpha plus beta equal to 1. Next, L to the power 3 alpha plus 2 beta plus gamma is to be equated to 0, which occurs as a power of L, and therefore we have the second equation. And similarly, t raised to the power this thing should be equated to 0, therefore we get the third equation. Now these three equations can be easily solved, and we find the value of alpha, beta and gamma to end up with this value of m. So the value of m is under root h cross c divided by capital G. Similarly, to find the value of L, here we have found the value of m. To find the value of L, what we have to do is we have to equate the second factor with this right hand side, and in a similar fashion we end up with three equations, 1, 2 and 3, and therefore that gives us L equal to under root gh cross c cubed. And to find t, we have to equate this equation with this one, and here we have t to the power 1. And in a similar way we have three equations, first one, second one and third one, and solution of these three gives us alpha, beta, gamma, from which we find the value of t equal to under root gh cross by c to the power 5. So what we have done is we have found the value of m, L and t in terms of h cross c and g, and the values are, if we put the values of h cross c and g, and simple calculation gives us this amount of value. Similarly for L, we had gh cross by c cubed under root. Putting the values we end up with this expression, which we will call LPL, the Planck length, and t is gh cross c to the power 5 under root. When we put the values we end up with this amount of value, which is TPL. So the Planck mass is this one, 10 to the power minus 8 kg. Planck length is 10 to the power minus 35 meter, and Planck time is 10 to the power minus 44 seconds. And expressed in terms of h cross c and g, they are of these values. So what we have done up to this much is we have derived the Planck units. Now from a study of natural units also the same thing can be obtained, which let me just go through it, let me just rush through it. From a study of natural units we got h cross equal to 1 and c is equal to 1 and these conversion factors, and we can switch over to Planck units using these values. Let us start with g, which is the universal constant of gravitation. So this is the value of g. Now the unit of g is m cubed kg second square, and in the lecture on natural units we had this conversion factor. So 1 meter is this amount of GeV inverse. So let us put it here to the power 3 because here meter cubed. Then we had 1 kg in terms of GeV, so instead of kg we have put it, and we have here second square, and second is this much GeV inverse, which we have put it here, and simple calculation gives us the value of G, and from here we can find the value of under root G to be 8 into 10 to the power minus 20 GeV inverse. Now in this value which we just now got, we have GeV inverse and we have this conversion factor, so we can easily convert this GeV inverse to meter to get to the Planck length. So the same Planck length also follows in this way, and this we have done using natural units. We can start with the same expression, under root G is 8 into 10 to the power minus 20 GeV inverse, and here instead of GeV inverse we can convert it back to second, and therefore from this conversion factor we end up with Planck time. So you see that under root G is LPL and under root G is again TPL, and this was done in the previous lecture, while the units of L and T were shown to be same in natural units. And if we start from under root g, the same expression, and then instead of GeV inverse, let us bring in kg inverse using this conversion factor, and then we end up with this relation, which is actually Planck mass. So 1 by root over g is Planck mass, while root g represents either Planck time or Planck length. So what we have done is we have derived Planck units. These are called Planck units, Planck natural unit or Planck scale. We have derived them starting from natural unit as well as independently. Now these Planck units were introduced by Planck in 1906, while Planck introduced in 1900 the Planck constant h. For a bit of academic interest, just let me show you certain important relations. This combination, Planck length cube divided by Planck mass divided by Planck time square, if we put in the values, then it turns out to be g. Here one thing is very important, that is mass of Planck mass. Planck mass is 2.2 into 10 to the power minus 8 kg. Now this value will show it is a massive value. It is 10 to the power 19 times larger than a proton mass. But on the other hand, this LPL, that is Planck length, which is 10 to the power minus 35 meter, is 10 to the power 19 times shorter than a proton diameter. And this time is extremely short, it being 10 to the power minus 44 seconds. Using Einstein's E equal to mc square concept, we can define Planck energy, which is here EPL is Planck energy, which is mc square, Planck mass into c square, and if we put the values, we end up with this relation. As mentioned right now, if we take the ratio of proton radius to Planck length, put their values, then we end up with 10 to the power 19, while the ratio of Planck mass to proton mass gives us 10 to the power 19. So this means that a proton is 10 to the power 19 times larger in size than Planck length, but it is 10 to the power 19 times less heavy than Planck mass. We can also define Compton wavelength. We know Compton wavelength is h by mc. Compton wavelength is h by mc, but reduced Compton wavelength is h cross by mc. So corresponding to Planck mass MPL, we can define reduced Compton wavelength, which if we put the values h cross, then MPL, for MPL we will put h cross c by under root h cross c by g multiplied by c. We end up with h cross g c cubed under root, which is actually Planck length. So this is one significance of Planck length, that it represents reduced Compton wavelength of Planck mass. We'll soon come to the most interesting part of the discussion, which is the significance of Planck unit. The theoretical physicists work with c equal to 1, h cross equal to 1 and g equal to 1, which means Planck mass, Planck length and Planck time, all of which being expressed in terms of h cross c and g are unity. So Planck scale units have numerical value 1. Now the next question is, why the Planck scale? Planck scale is used to know evolution of universe. It is a tool or a scale that is not biased, that is completely unbiased, that is not related to any particular mass, object, phenomena or situation, and it applies everywhere in the universe. Planck scale depends on only h cross c and g. So that is one significance of Planck scale. Since it is not biased, it does not attach to any particular object, it is the best candidate. These are the best candidate to describe a universe, in particular its evolution, interactions, etc. H cross corresponds to quantum phenomena, C corresponds to relativistic phenomena, while G corresponds to general relativity or gravitational phenomena. Now, using Planck scale means a union, we are trying to unite them, union of the three basic concepts of the universe. Planck units or Planck scale, as it is called, occurs in or are used in astrophysics, cosmology, quantum gravity, string theory, and such theoretical discussion or work. Now the significance. The significance of Planck units, we'll discuss it briefly. Time that a photon or light takes in order to move a distance Planck length can be easily calculated if we divide the Planck length, the distance, by the speed of light, and that gives us Planck time. So this is how Planck length and Planck time are related. Planck mass, Planck length and Planck time, that is the Planck scale, that define something which is called Planck Era. So suppose we have just used a diagram to indicate that this is a Planck Era. Actually these provide a boundary to a region. Now this region is actually a lockdown region for all our present theories. This is because within Planck Era all theories fail. So we cannot go into the Planck Era. We do not know what happened in Planck Era. So it is a lockdown region for all our present theories. Now what is LPL? LPL is of the order of 10 to the minus 35. LPL is the smallest length that is meaningful. It is the lowest spatial resolution. It is not legitimate or meaningful to ask what would happen if we go down still further. The question itself is meaningless. TPL or Planck time represents similarly the smallest period of time that is meaningful. We cannot think of a smaller time. So these quantities, Planck mass, Planck length and Planck time, they set a lower bound when we are in the observable universe, and they set an upper bound with respect to the Planck era or Planck region, Planck confines. Let us try to explain why we cannot go beyond Planck length or Planck time. Let us consider or think of Heisenberg's uncertainty principle, delta x delta p greater than or equal to h cross by 2, and this equation, which is an equation from special theory of relativity, E square equal to p square c square plus m0 square c to the power 4. Now when we go down to small lengths, say Planck length, that means we are making delta x very small. This again means from Heisenberg's uncertainty relation that delta p, that is uncertainty in p, becomes very high, and this automatically from this relation means that energy uncertainty is huge, so energy becomes infinite. Now energy infinite means Planck mass is needed to be of very large value, and as we emphasized earlier, this Planck mass is 10 to the power 19 times the proton mass. Such huge mass is necessary because of this relation, which follows directly from Heisenberg's uncertainty relation. Again, energy is infinity. This reminds us of a black hole. Black hole contains infinite amount of energy with event horizon as the radius, Planck length. And again, we cannot measure within a black hole. So it follows that we cannot enter into the Planck area. So talking about distances lesser than Planck length or a period of time lesser than 10 to the power minus 44 seconds does not have any meaning, because then that means we are inside the black hole and we cannot measure within a black hole. So we are unsure about Planck era. Let us mention a few points regarding the Planck era. It is thought that the universe burst into existence within the Planck era. Now, beyond Planck era, quantum theory, classical theory describe various aspects of physical reality. Now, there are certain unanswered questions. Some questions may appear to be silly. There are challenges which are to be addressed. Within the Planck era, the concept of space-time, does it hold water? Does it have any meaning? The distance, the time, do they have any meaning? The geometry of smooth space-time may suffer a disrupture within Planck era. The fate of this commutation relation x and y, which is we know to be zero, may not be so. Heisenberg uncertainty principle, which we have used widely here, may suffer a change within Planck era. Lorentz invariance, which we know it is true and is a consequence of special theory of relativity, it might also get modified in the Planck era. So in this lecture, what we have done is we have derived Planck scale or Planck units independently as well as from natural units. With the help of h cross c and g, we have been able to construct or define the Planck era, and we have mentioned certain significance of Planck era, and we have also posed certain questions which we say that we are not sure of. We also have cited certain terrible consequences or occurrences in the Planck era. For instance, questions like what happened before Big Bang do not hold water, because the concept of space-time, concept of distance, etc., they are challenged in the Planck era. Geometry of smooth space-time, that is also challenged in the Planck era. So it is not meaningful to ask those questions in the Planck era. At present, there are no established or accepted theories that describes the Planck era. I'll end up this lecture with two quotes. One is of a famous English novelist, Pratchett, who said, "The current state of knowledge can be summarized thus. In the beginning, there was nothing which exploded." And the second quote is of Stephen Hawking. "The realization that time can behave like another direction of space means one can get rid of the problem of time having a beginning, in a similar way in which we got rid of the edge of the world." Thank you.